going to jump back into atom structure and atomic mass. So, atoms are made up of three types of subatomic particles, and this is where we get more into why our periodic table is built the way it is. Atoms all are made up of protons, neutrons, and electrons. Protons are positive because they are pro-everything. Neutrons are nothing. They are neutral because they are neutral people. Electrons are negative because why not? Everyone else is sort of positive or nothing. I'll be the opposite. They're negative. Now, relative mass. Protons essentially provide a mass of 1. Don't worry about what that is, 1 gram, 1 microgram, don't worry, it's nothing. We're just calling it 1. There's no units here, we call it 1. It's one of the few times I'll ever say there's no units. Neutrons, what do they supply? 1. Same thing, 1. Electrons, what do they supply? Electrons supply 1 over 1,800. So you know what that means? That means absolutely nothing. They supply nothing. There is no mass that we say. So we say it's negligible mass for an electron, so they don't go towards the mass. The charge. The charge of a proton, positive, neutrons, neutral, electrons, negative. However, the charge are equal. 1 proton equals 1 electron in charge. So if I have 1 proton and 1 electron, they cancel each other out and I'm neutral. Really important. Despite the fact the masses are different, they are equal. Location is really important. Protons and neutrons are found in the nucleus. They make up the mass. Your mass is purely the nucleus of your atom. The electrons are found in the shells, which are surrounding the atom. So as you can see here, not too far, coming back, you have your nucleus in the middle here. So right here, this is your nucleus. Oh, I was on the wrong page. That's your nucleus. These are your shells. So notice how this shell has 2, this shell has 3. So therefore, given the fact that protons and neutrons are just wrong, there's probably more electrons around here. I'm not even going to say what this molecule is because it's probably just wrong. Nonetheless, but as you can see, this would be a non-full outer shell. It wants to have 8. It doesn't have 8, it's only got 3, so it's not happy. But nonetheless, as you can see here, this is your mass of your molecule. This is your relative atomic mass. That's where you get that from. So, your atomic structure and atomic mass. This is one of the points they talk about. They want you to talk about the basic structure, but they also want you to talk about how do I calculate the relative atomic mass? And you might say to me, what the heck does it mean by relative atomic mass? Why can't I just say atomic mass? Really good point. Relative atomic mass is because of this phenomena called isotopes. Now think of it like, I don't even know how to think about it. Just think about it like atoms. What is the best way to think about it? Let's talk about carbon for our main one. So carbon has 6 protons and 6 neutrons normally. So carbon is carbon. It's the 6th molecule on your periodic table. Being the 6th molecule on your periodic table, something I should have discussed before. Each of these molecules have their number, their atomic number. This atomic here. Their atomic number refers to the number of protons they have. So this has 3 protons. This has 4 protons. This has 5 protons. Carbon has 6 protons. Now, we learnt back on this last slide that the relative atomic mass of carbon is 12.011. Now, you might say to me, how the heck do I have 12.011? It's like, you're counting protons and neutrons, you're going to get a whole number. It's just like, you ask someone how many pets they have in their house, and they say 2.5. You're like, what do you mean by a half? And they're like, well, I've got a fish. It doesn't count. You have 3 pets. You don't have 2.5. So, you can't have an odd or a decimal number of protons and neutrons. So then you say to me, well, how the heck did I get 12.011? Well, it's because it's relative, and relative refers to isotopes. So isotopes are essentially atoms of the same element that have a different atomic masses. So carbon, there is so much carbon in the world. You'd have bazillions, you have trillions of carbon atoms just in you yourself. Outside of that, there are unfathomable numbers of carbon atoms around the world. Unfathomable. You cannot even just consider the number. There are so many. So given that idea, not every single carbon is going to have the exact same number of neutrons. It just isn't possible. Yes, every single carbon has the same number of protons because if it had 13 protons, it's not carbon. That's a really, really important fact. You might say to me, well, what about the proton? Well, then a carbon might have a different number of protons. Well, then it's no longer carbon. It's a different atom. The atom is dependent on the protons. Really, really important. But nonetheless, every single one is going to have, they're going to have different numbers of neutrons. So what we like to think with carbon is as a generalization, we've sort of taken massive quantities of carbon and we've figured out generally what are the percentages of each. We don't know exactly, but we know to a pretty high degree what there are. And we know that about 99% of carbon is carbon-12. It has 6 protons, it has 6 neutrons. We also know that about 0.8% of carbons are carbon-13. So they have 6 protons and they have 2 neutrons, and they have 7 neutrons. And we know very, very small number, it's like 0.1 or 0.2% of all carbons are carbon-14, but they have 6 protons and 8 neutrons. So when you make that a relative atomic mass and you do the maths as to what is the average over the 3, your average is 12.011. That's why a lot of people will just refer to carbon as 12. Their atomic mass is just 12. They'll simplify it down. But if you want to be really nitty-gritty, you get a relative atomic mass of about 12.001, which is really, really very close to 12 because most of them are 12. So that's because of isotopes. So isotopes are those different variations. The radioisotopes are isotopes that are unstable and decay radioactively. Carbon-13 and 14 are examples of that. They're not very stable, and that's why there's low percentages of them. So as we said, they're different forms of atoms of an element with the same number of protons and electrons but different number of neutrons. Isotopes have the same chemical properties because they have the same number of electrons but different physical properties due to the different number of neutrons. You can then be stable or unstable. So stable isotopes do not undergo radioactive decay, so it doesn't emit radiation, but unstable isotopes do go under radioactive decay and they will emit radiation. So it's one of those aspects you do need to know about the difference between the two. Isotopes, essentially atoms of the same element, as you can see there. This is what I was talking about earlier. You've got your carbon-12, carbon-13, carbon-14, and if you look at your protons and neutrons, your protons 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, neutrons 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8. Exactly what I was trying to talk about, and that is why these are isotopes. So different isotopes are found at varying amounts. As you can see here, these are the exact percentages I was looking for, the ones that I was more likely to do. But as you can see that we assume that about 98.9%, wasn't 99%, but close to, of carbon is 12, whilst 1.11% of it is carbon-13. And then, as I said here, carbon-14, such a small percentage, I thought it was like 0.1, but maybe it's way, 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 way less, is because it just doesn't exist. It's very unstable. So as you can see here, isotopic elements, you write the element, you write the mass number, you write the atomic number here. So you will write your elements a bit differently for this. So you'll write, carbon-13, 6. Carbon-13, 6, carbon-14, 6, carbon-12, 6. So each of your isotopes, you need to be able to write them out differently. So as you can see here, carbon-14 is a radioisotope. As I said here, that's an example of it. You already know what radioisotopes are. I've discussed a bit. Now, there's also decay. This is one thing that slightly alters from VCE to HSC, but I have been through this before at a university level, so it should be pretty fine. Essentially, you have alpha, beta, and gamma decay. Now, gamma decay is the one that's really, really harmful. It's really dangerous to be around gamma decay, gamma radiation a lot. That's things like, I believe if I'm thinking correctly, these are things such as like our nuclear power plants that have melted down. So there's one in Japan, and you have like Chernobyl is another example. They emit gamma radiation. Now, that's why we've built big concrete things around them. They also do produce a bit of alpha and beta. The concrete kind of gets rid of the alpha and beta. The gamma radiation, there's not a lot you can do. We sort of lead plate as well as we can, but it's pretty hard to get around. But essentially, alpha decay occurs in isotopes of the heaviest elements to remove mass, i.e. when there's too many nucleons. So what they'll do is they'll remove a neutron, but essentially it's really the heavy elements. They don't really care too much about it, so they get rid of something that's pretty heavy. Being so heavy, they have a really strong ionizing power, but their penetration power is terrible. So if they do hit something, they can do a bit of damage, but they can't penetrate very well. So therefore, you can get a sheet of paper and the neutron's too big to get through. So it's just going to get stopped. Beta, on the other hand, it's an unstable nuclei that contains too many neutrons, and electron is emitted as a beta particle. So essentially what we do is we actually emit electrons instead. So because we have too many neutrons, there's issues with the mass and so forth. They actually emit an electron first. They then sort of move to alpha decay afterwards, and they go, all right, I'm sick and tired of this neutron, and get rid of it. This just emits an electron. As I said, electrons are a lot smaller, therefore you actually need sort of a metal plate to stop it. So aluminium it's not very dense, but it's dense enough. And that's what's going on there. Where gamma radiation is energy. We're not actually emitting anything, we're just emitting energy. And because you're emitting energy, it's really hard to stop. And therefore you need like a really thick plate of lead. Lead has a really high density and a really high ability to absorb energy, but you still need it really thick. So essentially what it is, it looks like this. So that's gamma. And essentially gamma is just really high level energy. It's got really high penetrating power. It just has low ionizing power to really high penetrating power. It's what makes you very sick. You experience a lot of this. It's really unhealthy. You don't want this to occur, and therefore that's why it's really dangerous. So as you can see here with alpha decay, as you can see here, alpha decay causes the atomic number to decrease by 2. So you go A4 to Z2. And the mass number to decrease by 4. So alpha particle is the equivalent to a helium nucleus. Beta, on the other hand, occurs when there is an excess neutron. So a neutron decomposes into a proton and an electron. Essentially, the atomic mass increases by 1. And then gamma radiation particles are released. Gamma particles are released when the atom has too much energy. Due to being energy, there is no change in the atomic mass or number. So, radioisotopes, we've already discussed this. They can be helpful in many real-world situations, such as imaging, historical dating, medical treatments, etc. The reason they're really useful in historical dating is because we understand that they have half-lives. So there's the half-life of a lot of radioisotopes is really long. We're talking tens of thousands of years. After tens of thousands of years, half of the amount of radioisotope you have in a sample, or you expect to have in a sample, should have reacted, should have emitted off its radiation and gone. It should have emitted what it needed to and stabilized itself. So over time, you can take samples and go, all right, well, there's this much. I should have had this much if it was at 100%. Therefore, I can tell it was this old. So that's sort of how you do it. Carbon-14 is a man-made isotope, so it's extremely rare cases where it occurs naturally. Undergoes beta decay, used in carbon dating, so useful for estimating fossil ages. As it says man-made, it's because it comes from fossils, it comes from humans. So it is sort of still occurring naturally, but one of those things. The other one that's really cool is uranium-238. It's a naturally occurring radioisotope. It undergoes alpha decay, and it's used for making nuclear power and generating nuclear power. But the problem is the way that we work with it ends up producing a bit of gamma, and it gets really dangerous. So what are atoms like? What do they look like? So now that we've gone through a bit of decay and what's going on, what do atoms actually look like? So we like to look at what we refer to as Bohr's model. Now, none of you should have seen this movie being in year 11, but I'm sure some of you might have gone with your parents. And you may have seen the movie Oppenheimer. The Bohr that they actually discuss that he meets when he is at university in Germany, when he goes to Germany when he's younger, is actually Neil Bohr. It's the same bloke. This is his theory. So it's kind of cool. For me, that movie was actually kind of cool in terms of seeing this. I was like, wow, these are people that, I've learned what they are discussing. Yes, they are just actors playing them, but at the same time, it's cool seeing that, real life history being played out. But essentially, in Bohr's model of an atom, there are fixed energy levels that electrons are found in, and these are known as electron shells. So electrons move from a lower energy to a high energy when they absorb energy. This is known as excited, and when excited electrons immediately return to their original or low energy levels known as ground state. So essentially what they do is they move up really quickly and they move back down really quickly. So they go up, oh, I'm excited, oh, I'm back. It's like an immediate up and down. In this process, they release that excess energy that they absorb. So they absorb energy and they move forward and they go, actually, I don't want this energy. They go back and they release it. That released energy comes out as light. And you can sort of read what light energy is coming out and say, all right, it was this color or it was this intensity, therefore I can say that I'm working with these levels of energy in these shells. It's actually something you can do. So as you can see here, you've got 3 shells here. You've got some energy that hits an electron. You've got a lower energy state. You've got a high energy state. The electron moves up into an excited state. It goes, oh, I'm really excited right now. I've got a lot of energy. I move forward. So it moves into this excited state. And then it goes back down. And when it goes back down, it re-releases the energy, but it transitions it into a sort of a light approach. So now it's like acting as a light. So this energy has gone up, and now it comes back down, and it goes, all right, I don't want this energy anymore. I'm getting rid of it. And it gets rid of it the best way it can, and it does that by emitting light. So, as you can see here, there are a whole bunch of shells that you need to know, and the number of electrons that are in them is determined by 2 times n squared. So, if I say I have 2 shells, I go 2 squared is 4, 2 times 4 is 8. If I go, all right, now I have 3, so I go 3 squared. 3 squared is 9. 9 times 2, 18. Now I have 4, so I go 4 squared, that's 16 times 2, I have 32. So the max number of electrons changes depending on the number of shells. However, you will only ever really work with 4 shells, and your 4th shell, you will only ever really work up to 2 more. So you only work up to about 20 electrons usually. You can go further. You will discuss it at sometimes in some occasions, but most of the time you're maximally going to go to 20 electrons. So you're going to go max in the shell is 2, max in the outer shell is 8, max in the outer shell is another 8, and then so forth. But we'll discuss this in a second. But as you can see here, this is sort of what we were discussing. This is Bohr's model. So his model can only explain the emission spectra of one element, hydrogen. And there are a lot of assumptions in this model which he could not explain, but could sort of prove most of them to be true. So we switched to sort of Schrodinger's model. So Schrodinger's was the next model to come along. Schroeder essentially took Bohr's model and he improved it with quantum mechanics. So he kind of went to the next level. So electrons are now considered to have a wave-like property. So if those of you have done physics, and this is the reason, this is a sort of a very technical part of chemistry that you don't need to know in super duper detail. But what you'll find is that in physics, you discuss this idea that light and particles act both in a wave, but also not in a wave. And it's kind of this hard idea to get your head around that they have properties of both, and you're like, I have no idea what's going on. Don't worry. Scientists who have studied their entire life still don't know what's going on. You don't need to figure it out. But electrons are thought to have a wave-like property as well as just a physical property. And so he suggested that the electrons were not in orbit, but rather they were in a cloud in regions of space, which we called orbits. Now these orbits, he still referred to as shells. So he said, all right, they're in a shell. This is the major energy within the atom. But they also have subshells. And these are energy levels within these shells. So you have an S, a P, a D, and an F. There's a lot more, but these are the first couple. And then you have orbitals. So orbitals are essentially the regions within these subshells where electrons are found. Now, you don't need to know about orbitals. Probably a bit too far. You're not going to discuss them all that much. But as you can see, this is sort of what we sort of looked at. These are energy levels. And then these are sort of where they were in their shell. So this is in the second shell, the third shell, the fourth shell. And we sort of discussed that from there. So we can represent the subshell using box notation. Essentially what you have is you have 1s, 2s, 2p, 3s, 3p, so forth. So each box contains 2 electrons. The arrows represent the electrons with 1 in the up position and 1 in the down position. The S subshell has 1 box. The P subshell has 3 boxes. The D subshell has 5 boxes and the F has 7. This is due to a different principle which states that each orbit can contain a maximum of 2 electrons. It's also because we like to pair electrons, and electrons like to pair up. Now, it's something you will learn as you go through chemistry, but electrons pair up. They do this thing where they pair up with each other. Now, what's also really important is that there's like an order to this stuff. And essentially it goes 1s, 2s, 2p, 3s, 3p, 3d, and then you go back to sort of like 2d. no, sorry, you won't go back to 2D. And then you'll go, so you go 3s, 3p, and then you'll go 4s, 4p, and then back to 3d. So you're not going to have to worry about that too much because it's not something you're going to discuss. It's not something you're going to go to. But at this level, you need to understand the order is 1s, 2s, 2p, 3s, 3p. Really important. That's the order in which the electrons fill. So they're going to fill 1s first, then 2s second, and then 2p next, then 3s, then 3p. So I want you to have a go at these. So write the electron configuration for carbon using SPDF notation. As you can see here, we've already gone ahead and done that. And it says draw the electron configuration of carbon using SPDF box notation. So we've already done the first part for you. This is the SPDF notation. So it's 1s squared because there's 2 electrons in it. 2s squared because there's 2 electrons in it again. So S, again, is the subshell. 1 is the main shell. And 2, the number at the top, to the power of is the number of electrons that are in that sort of subshell. 2s, same thing. 2p, same thing. Except this time there's 2. Well, it's p, and there's 2 again because we only have 6 electrons because it's the 6th element, so 6 electrons. So that's why we get that 2 there again. Now, I want you to have a go at drawing the electron configuration of the carbon. So you've been given using the box notation, sorry. So you're going to use the box notation. We've already done the SPDF notation. I want you to give the box notation. And then I also want you to do it for silicon. Now I want you to do both for silicon. We're not going to give you this part for silicon. Best way to go about this, if you don't have a periodic table up, get one up. Just search it up, periodic table. Or you're welcome to pause the video here on the periodic table. I'm giving it to you here. So you can figure out where silicon is. You can figure out how many electrons it's going to need, etc. But the best way to go about this question is for you, I want you all to pause and then come back to it. I'm just finding the question again. Here's the question. So what I want you to do is pause. I'll give you a little bit of time. Take a couple of minutes to do this question and then unpause and I'll go straight into it so there's no gap in the recording. But 3, 2, 1, pause. And hopefully you're back. So hopefully you had a go at that question. Hopefully you took a couple of minutes. Nonetheless, we're going to go through it. So first of all, we've already done the carbon SPDF notation just here. But this is what it looks like when you do the box notation. So what's really interesting about this box notation is that you're going to fill the up arrows first. It's something we didn't discuss initially. So you might have got that wrong initially, and I do apologize, I didn't really discuss it. But you do the up arrows first, and then you do the down arrows. So you always fill the up arrows in your P first, and then you do your down arrows next. So if you did up and down, that's okay, I understand, but in this case, you do your up arrows first. So therefore, for silicon, it would be very much similar. Your P is going to have your up arrows first. As you can see here, you've got 1s, 2s, they're both squared because there's only 2 possible. Then you go to your 2p. Now there are 6 possible, so you put 6 squared. You then go to your 3s, there's only 2 possible, so you put your 2. Then you go to your 3p, and there's actually only 2 in there, so you put your 2. So most of these are 2s, there's 1 6 in there, but that's only because you couldn't fill this one anymore. So as you can see, this is the order in which you do it. This is the order in which you fill. So you go 1s, then you go 2s, then you go 2p to 3s, 3p to 4s, 3d to 4p to 5s, to 4d to 5p to 6s. So that is the sort of Pauli principle. It's also sort of these other 2 principles or these other 2 rules. These also sort of discussed it. The thing was, at this period in time, it was such a race in chemistry. So everyone was producing theories at the same time. You're going, this is the right theory. No, this is the right theory. No, this is the right theory. No one wanted to work together. Partly because of wars, partly because of political differences, but no one wanted to work together. So because of that idea that no one wanted to work together, everyone just claimed it. So therefore, there is different principles and rules that state the exact same thing that everyone sort of listens to, and everyone goes, all right, we don't really want to, pick one person over the other. In science, it's very much like if they all figured it out at the same time, then they all should be credited with it. So we give things multiple names. This is one of those things where we give them multiple names. Their rules are slightly different, but pretty much saying the same thing. This is how you fill your boxes. So here's a question here. Which of the following is not a method that can be used to separate homogeneous mixtures? So revision. So as you'll see throughout these slides, there's going to be a bit of revision. We're going to jump back and forth. That's because I want you to sort of touch on what you just did It's a good learning method, and it's something we'll discuss later on as a really good learning method. And this is a really good point in time just to sort of take that pause and go, all right, we're about, a bit over 70 minutes into this. This is this point in time where we go, all right, let's do some practice questions, let's punch something out, and then we'll push into this last. We really only have about 35 minutes left after these questions, so hopefully we'll be done just under 2 hours, but you'll see that after this we've got bonding, and bonding shouldn't take us more than about 30-35 minutes to go through. So, which of the following is not a method that can be used to separate homogeneous mixtures? All right, I want you to take a second. 3, 2, 1, pause, and hopefully back. So hopefully you paused, hopefully you had a go at that question. Shouldn't have taken more than about a minute. So remember, when we went through this, you want to separate a homogeneous mixture, we need to use one of the first 3 methods. So we needed to use the evaporation, the filtration. So filtration got rid of the solids, evaporation got rid of the liquid and left the solid, and fractional distillation did the 2 liquids. Decanting is a little bit different. This is more for heterogeneous mixtures. So as you can see here, you cannot pour off the top as something is evenly dispersed. Because they're evenly dispersed, you cannot use decanting. All right, now we have another one. So we have explained where each of the following elements would belong in the periodic table. So a malleable and lustrous solid, an unreactive gas, a soft solid that reacts readily with water, a brittle solid that conducts electricity and heats fairly well. So what types of, what parts of the periodic table are going to explain each of these? So I want you to have a go at this question. I'm going to give you, this question should take you around, look, you've got two marks for each. Give yourself a minute and a half, if not 2 minutes for each question. You probably should get on a flow and finish it a bit quicker than, 8 minutes. But, give yourself at least 5 minutes to get through this. If not, take up to 8. Have a go at this. Take your time. I'll give you time to pause now. 3, 2, 1. And hopefully you're back. So, as you can see here, you've got a malleable lustrous solid. You've got an unreactive gas. You've got a soft solid that reacts steadily with water. So this is solubility. You've got a brittle solid that conducts electricity. So if I was going through this, the first one I'd think about is unreactive gas. Unreactive gas. We talked about it. Which of the gases does not want to do anything? Which of the gases is really comfortable with who it is, doesn't want to share anything? Noble gas. Malleable lustrous, what are we going to talk about? We're going to talk about metals. Solid, a soft solid that reacts readily with water. It's an interesting one. You probably think like non-metals, metalloids. There's a few different ones you can think about there. We'll discuss that in a little bit. And then a brittle solid that conducts electricity and heat fairly well. Again, we're probably looking at metalloids, something that we'll discuss. As you can see here, this is how they discussed it. Now, if your answers look very different, don't worry. This is a really weirdly worded question in terms of this is not a SAC level or an exam level question. It's more about just pushing your learning. So, a malleable lustrous solid is towards the left of the periodic table amongst the metals, likely in group 2 since group 1 metals are too reactive to be malleable. That's a little fact I wouldn't have expected you to know at this point in time, but it's a good one to learn. These are great questions for learning. An unreactive gas. So an unreactive gas is on the right of group 8 with the noble gases, since this is the group of inert gases. Should have known that. That was a pretty straightforward question. This one here says likely group 1, since elements on the left of the periodic table are softer and are most reactive are the furthest to the left. So that's probably what you're going to be thinking there. A soft solid that readily absorbs. That's a pretty decent answer. And then a brittle solid that conducts electricity. Left of the non-metals, since metals are malleable and conductive while non-metals are brittle and non-conductive. These mixed characteristics make it a metalloid. So as you said here, a metalloid is sort of just in between metals and non-metals. And then these are the other ones here. So these are tough questions, but they're not exam-style questions. These are the sort of questions that you would do sort of throughout the year just to solidify your learning and just to even use them as a learning point. Like some of these points I may not have even known as well if I hadn't read through these questions. So it's a really good point to just sort of learn. All right, another multiple choice. We have a student conducting an experiment to measure the amount of gas generated when different masses of reactants were mixed in 100 ml of water. The experiment is shown below. Which of the following correctly identifies the variables of this experiment? So I want you to have a go at this question. I'll give you your time now. I'd say this is maybe a 1 to 2 minute question. If you need more time, feel free to take it. But again, 3, 2, 1, pause. And hopefully you're back. So, which of the following correctly identifies the variables of the experiment? So, it says here that we want to conduct an experiment to measure the amount of gas generated from different masses. Different masses. We are changing that. So mass of reactant is your independent variable. So you can rule out B and you can rule out D. You're left with A or C. Then it says that your dependent variable is temperature or volume of gas collected. Well, we are measuring the amount of gas. It says in the question, measure amount of gas. Remember, the dependent variable, you're looking at what you're measuring. So you're not measuring temperature, measuring volume of gas. I think my answer here is C. Let's just check a control variable. Well, we want to keep the temperature the same because we don't want the temperature to manipulate how much gas is being produced. So therefore, temperature will be a control variable. C is your best answer here. C. All right. Question 10. Write the SPDF configurations for each of the following. So aluminium, chlorine, fluorine, sodium, iron. Again, use your periodic table. Again, you should have one up. If you don't have one up, give me 1 second and you can quickly pause the video at this point here. You can quickly pause and do each of your SPDF configurations. But if not, come back to here, have a go at this one here. You've got A, B, C, or D. So you've got these three here. Have a go at this one here. And pause the video in 3, 2, 1. Pause. And hopefully you're back. So hopefully you're back and you had a go at this one. Again, just use the periodic table. It's a pretty straightforward sort of way of doing it. So you've got aluminium, chlorine, fluorine, and sodium ions. Again, look at how many protons I have that have the same amount of electrons. So aluminium here has 13 protons, so therefore you're going to have 13 electrons. So you're going to do your 1s2, 2s2, 2p6, you're at 10 now, 3s2, 12, 3p1. Chlorine, on the other hand, has 17, I think it is. So 2, 2, and 6 is your 10. Number 2 is 12, and then 5 is your 17. Fluorine has 9, so again 2, 2, and 5, and your sodium has 10, so 2, 2, and 6.